All right, we're continuing with our series in Chapter 3. This time, Section 3.3, Properties of Functions. So the properties that we just want to call out of a function are the functions even? Is the function even? Is it odd? Or is it neither? Now, even and odd isn't the same thing as numbers being even or odd. But I do want to point out that you know of examples of numbers that are even, like 4, a number that's odd, like 5, and a number that's neither, like 1/2. There's nothing wrong with a number being even, odd, or neither. Functions can be even, they can be odd, and sometimes they're neither one. And just like numbers can be even, odd, or neither one. Generally, fractions and decimals are not even or odd. They just don't qualify. So we're going to talk about functions being even, odd, or neither. Going to talk about graphs and what it means for a graph to be increasing, decreasing, or constant. So this whole thing about, well, maxima and minima, kind of, I guess, Latin for maximum and minimum values in a function. By the way, we're not really good at this until calculus. So again, this is one of those foreshadowing ideas. But absolute maximum, absolute minimum, we'll get to talk about that a little bit. We're not going to do anything with graphing utility, so that's completely crossed out. Not completely, I have one slide where that still remains. But average rate of change is another idea that will definitely you'll need to know. All right, so let's get into it. First idea is if you can do this with a function, start with f of x. I'd like to write it this way, or f of minus x. And you go through a process. So the dot is you go through a process and you get right back where you started with. You get right back to f of x. You put in f of minus x and you can just think the minus goes away. Then you have an even function. So for example, if the function were absolute value of x, let's run the test. F of minus x would be the absolute value of minus x, but that's the same as the absolute value of x. It's not x. I can't just drop the absolute value, but I can drop the minus sign inside the absolute value, and that is the original function. So this logical progression to starting with f of minus x and finishing with f of x is the proof we need to verify that a function is even, at least with this method. A function is odd if you start with the same idea, f of minus x, and you get the function back. I'll give an example here. Let's say I had f of x equals x cubed. So that would be minus x cubed, which is literally minus x, minus x, minus x. So notice the 3 minus signs. But if I have 3 minus signs, I can shrink that down to 1 minus sign because, you know, minus times minus makes a plus, but 3 minuses, I still have 1 minus. And back to x cubed because I have 1, 2, 3 x's. So do you see it? I have a minus in front of my original function. If my original function were, looks like I had a minus there. If my original function were x cubed, then f of minus x is minus f of x. So the process led me, I mean, I had to work at it a little bit, but the process led me to concluding that when I put in a minus sign, it's like I just have a minus sign outside of the argument. So this would be an odd function, f of x cubed. When you graph a function, and the book uses this extensively, when you graph a function and you know it's even, then you know it is symmetrical with respect to the y-axis. So even means if you have a point here in quadrant 1, you have its mirror image here. I will, use this. All right. A function is odd if you have a point here and its mirror image would be here. And we've seen this in another section, so you've heard me talk about this before. All right, so if we look at this graph, it's neither even nor odd. So yeah, if I have a point here, I see another point down here, that doesn't qualify. It has to be, if you have a point here, since there's no point of the graph here in the other side of the y-axis, it's certainly not even. And if I go to the origin and keep on going the same distance that I traveled here, in other words, I go to the origin, I'm halfway, I come over here, I would need to see a point right here to convince me that it's odd. So since there's no point here, it's also not odd. And that certainly can happen. A function can be neither even nor odd. So here are two examples of functions that do show symmetry. If I pick any point here, there's a mirror image on the y, through the y-axis. So if it's symmetrical with respect to the y-axis, remember the connection, it's even. If it's symmetrical with respect to the origin, it's odd. So let's say you don't have a picture, but you have the equations. How do you know if they're even or odd? Well, it has to do with that function. You always start with f of minus x, and you work it and see if you get back what you started. See if you can get back what you started and get f of x. And if you can, f of minus x equals f of x, the conclusion is the function is even. In this case, same idea. I start with, well, they're calling it g because they don't want to use f in the same problem. All right, twice in the same problem. So g of minus x, start with that, work with it, and they continue down here, but work with it, and you know what? We're not going to get, I can factor out a minus, which is what we try to do, but notice I don't have minus g of x. I don't have minus parentheses that. Right? The signs are different. So it didn't happen that it didn't equal f of x, didn't equal minus f of x. So yeah, once again, neither even nor odd. I'll just look at one more. I think I already did absolute value in a different way. So let's look at this one here. So I'm not saying absolute value is just going to be the same because the way they changed it, it might no longer be. I think it is. Yeah, it still is symmetric. But all right. So in this one, because x occurs twice, I have to substitute twice. We have to go through the process. But notice how h of minus x equals, well, minus h of x. Which is what? Our conclusion that the function is odd. So this function was odd. There was another function with a cube in it that wasn't odd. You kind of have to run the test. All right, we like to talk about functions as increasing, decreasing, or constant. And when we talk about a function, we're always reading it from left to right, like an ant walking on the function from left to right. I have to point that out because a lot of students will look at one of our favorite functions, the, square root of x, and they'll mistakenly conclude that it's increasing. And I tried to, put arrows here to make it look like we would say it's increasing. No, not from the perspective of going from left to right. As I go from left to right, it is decreasing until it gets to a certain point, and then it starts to increase. And that's exactly how we would describe this. It's decreasing on one interval, and it's increasing on the other interval. That yellow line here is where it separates from decreasing to increasing. So they didn't give us anything that complicated yet, but on the next slide I'm sure they will. But here this function is always increasing because the ant's always going uphill. Here we're always going downhill. Here it's constant. So hopefully you can see it. Yeah. There's a little blue here. It's constant. It's increasing. It's decreasing to a point, and then it starts to increase. And they're going to talk about each of those intervals, one kind of slice at a time. So this interval on the x-axis, it's literally on the x-axis, but it's constant there. This interval here, and the reason why I'm painting the x-axis is that's how we describe where it is increasing. So it's increasing, but I'm just looking here. It's increasing on the interval where the minimum is -2 and the maximum is 0. Then it decreases all the way from, well, it looks like it increases again from 3 to 4. So they're a patch where it's increasing. The ant's going uphill. But the ant's going downhill from 0 to 3. So 0 to 3, the function is decreasing. So if you have the image, and that's one of the important things, we kind of need the image. If you have the image, you can tell where the function is increasing or decreasing. The extreme value theorem, very important rule in calculus. And so it's not really much we're going to do with it here, but just pause on that. But let's look at this formula. Again, it's a formula you're going to need to know. And by name, average rate of change formula. Zoom in on that. And it's the average rate of change between 2 points. So from 0 to 1, there's an average rate of change from x equals 0 to x equals 1. I'm ignoring these for now and just looking at this. So the slope of this line is the average rate of change from, I'll call it point A to point B. Now, they did say from 1 to 2. So there, and that's a totally different point, a rate of change. I mean, it's going much steeper from point B to point C, and then somewhere in between from point A to point C. So that's basically what they're asking is the average rate of change is geometrically, how steep is that line? But let's look at it. Let's look at this one here. From 1 to 2, so do you remember the formula? It was f of, from A to B, it's f of B minus f of A over B minus A. And so if B is 2, it's f of 2 and 2 minus 1. And because A is 1, yeah, put in a 1 there. And notice they drew it here. That's not my drawing, although it looks kind of like one of my drawings. That is the slope of that line. So you find out the slope is 3, or the average rate of change is 3. Well, anyhow, if they give you the same function, but they give you, whatever A and B they give you, you're just going to plug it in and calculate that slope. Again, this is more of an idea from calculus. The average rate of change of a function from A to B equals the slope of the secant line containing the 2 points. So basically what they're saying is you could use a different technique. You could use y2 minus y1 over x2 minus x1 and just find the slope when they ask you for the average rate of change. So average rate of change is just a reworking of a slope formula that you might have already memorized. All right, so we'll get to the work on this one. Now, I'll show you the graphing utility, but you're not going to be expected to ever use a graphing utility. They just made a graphing calculator. All right, so no surprise, they went ahead and did the calculation. They had to calculate what g of 3 was and what g of 0 was. But they did the work, and they found out the average rate of change was 1. So it's a number. It's the slope 1. And well, we'll just get to the image here. Well, so basically what they're saying is if you used the slope formula and solved, you'd also find the secant line, which is the equation of that entire line. Not something for us to do really, but I just wanted you to see what they did here. So they're saying, you know, if you just take those 2 points, they have to be those 2 points, you will get not just the slope of the line, but they're actually having the graphing calculator draw the line. That last part you don't need to know. So let's go back to the last thing you do need to be good at, and that is average rate of change. Plug it into the formula, and should be able to calculate that slope. And all right, that is, let's go back to the beginning. I know it's, sorry, I know it's a little hard to look at all those screens going by fast. But I just want the title screen of this section again, because it was a fairly long one. I forget where we are sometimes. Nope, we are in section 3.3. That was properties of functions. Once again, even, odd, and the major thing we did here was even, odd, and the average rate of change formula for your homework. All right, and that is section 3.3.